Greetings everyone. My name is Daniel Schilliger. I am from the Technical University of Ilmenau in Germany, and today I will show you that dropout is not all you need to prevent deep gradient leakage. In federated learning scenarios, multiple clients leverage their private local training data to collaboratively train a globally exchanged machine learning model. To do this, a central server instance sends the current model state to the participating clients. Initially, this model state is usually randomly initialized. When the clients receive the current model state, they locally train the model with their own private training data. The clients then send the accumulated local training gradient back to the server. When the server has received the gradients of all participating clients, it aggregates them and updates the model. This process is then repeated until the training loss converges. Although the central server might honestly participate in this training process, which means that it basically does not interfere with the training process itself, the server might be a curious one. In this threat model, the curious server is interested in gaining knowledge about client-specific features, or more specifically, it wants to gain access to the private local training data of the clients. Now, recent work on so-called gradient inversion attacks has shown that with the knowledge of the model state and the exchanged training gradient, such an attacker can fully reconstruct the local training data of the corresponding clients. This represents a serious threat for data privacy. Of course, there's also lots of research going into defense mechanisms that aim to prevent such attacks. For one, there are cryptography-based methods like homomorphic encryption and secure multi-party computation. However, these are computationally quite expensive and have certain limitations. Hence, a lot of work in this area focuses on introducing some kind of stochasticity into the data, the exchanged gradients, or the training process itself. However, research has shown that these result in an inherent trade-off between model utility and data privacy. Some observations in recent work suggest that adding dropout as a kind of privacy-inducing module to the model might be a possible candidate to protect data from reconstruction. And as you can see in this example, that actually seems to be the case. However, in our work, we proposed a novel dropout inversion attack and show that dropout alone cannot sufficiently protect the data from being reconstructed. To give you a short outline of the next 12 minutes, I will first go into some more details on how gradient inversion attacks generally work. Then I will try to give you an intuition of what happens during the attack optimization process when the attacked model uses dropout. After that, we test our gained intuition by conducting a small thought experiment and giving the attacker a little more knowledge than it should actually have. From these insights, we then derive our proposed dropout inversion attack, and finally I will give you an overview of our experimental setup and present our results. But first, let's start with gradient inversion attacks. So as you hopefully remember, the attacker aims to reconstruct the training data of a client with the knowledge of the model state and the local training gradients. To do this, the attacker first randomly initializes some dummy data. The dummy data is forwarded through the model to calculate a dummy training gradient. The goal of the attacker is then to iteratively adjust the dummy data so that the dummy gradient matches the training gradient of the client. Hence, he calculates the distance between the client gradients and the dummy gradients. Usually, L2 or cosine distance are used as a distance function. Some specific attacks also add a regularization term omega to the so-called reconstruction loss. The attacker then calculates the gradients of the reconstruction loss with regards to the dummy inputs and targets and updates the dummy data accordingly. This optimization process is repeated until some termination criterion is fulfilled. At this point, it is very important to note that the attacker and the client use the very same model F for forward and back propagation. This is because the client uses the model state it received from the attacking server for local training. So now let's look at what exactly goes wrong with the attack when the model uses dropout. As dropout introduces stochasticity into the training process, each forward propagation step applies a different set of dropout masks to the intermediate feature representations. Hence, the model F is now a stochastic function that depends on the dropout masks applied during forwarding. We denote the specific realization of masks that the client applied during a forwarding step with psi-c. In the upper row, you can see a schematic representation of such a realization. The x-axis denotes a single mask for each layer, while the y-axis denotes the mask values that are applied to the activated neuron outputs of a layer. White tiles represent a 1, while black tiles represent a 0, which means that the corresponding neuron connection is cut off. The lower row correspondingly represents the feature outputs after activation and application of the dropout masks. On the right-hand side, you can see how the reconstruction loss behaves during the attack optimization process for a vision transformer and some samples of the Cypher10 dataset. Below that, you can see the progress of the reconstruction illustrated with one sample image. The blue line here represents the baseline gradient inversion attack, where the model uses no dropout. In this case, the dummy gradients quickly converge towards the client gradients and the data can be reconstructed successfully. As the attacker has no knowledge of the specific set of dropout masks the client used during training, he basically has two options. The first one is to simply ignore the fact that dropout was used during training. That means that the attacker uses no dropout or a dropout rate of 0 when calculating the dummy gradients during the attack optimization. This is represented by the orange line. Here the clients used a dropout rate of 0.25 and the attacker ignored that dropout was used during the attack optimization process. As you can see, the reconstruction loss is not able to converge as soon as dropout was activated. The second option is to use the random dropout. That means that in every step of the attack optimization, the attacker uses a new random set of dropout masks psi. Looking at the plots on the right, you can again observe that the very same behavior is happening. The reconstruction loss is not able to converge as soon as dropout was activated. Now, in both cases, there's one major problem. The dropout masks of the client and the attacker are different, and it is extremely unlikely that they will actually be the same at any point during the attack optimization process. Hence, the attacker is forced to base the attack optimization on a model realization f-psi that is different from the realization f-psi of the client. This in turn causes a mismatch between the calculated dummy and the client features, as well as the resulting dummy and client gradients. So what would happen if the attacker knows the actual realizations of the client model? If the attacker has knowledge about which dropout masks were used during local training, he can use the very same masks during forward propagation of the attack optimization process. Therefore, the dropout-related 0 values in the client and dummy gradients match by default, and it is easier for the attacker to minimize the gradient distance again. As can be seen in the plots on the right, the attacker again can fully reconstruct the client training data if he has the additional information on the client dropout masks. Of course, in reality, the attacker does not have this knowledge. But how can we still make the attack work? We argue that if the attacker finds a close enough approximation of the client dropout masks, he still bypasses the privacy-inducing effects of dropout. To find a model realization for the attacker that is similar to the one of the client, we propose to optimize the dropout masks psi that are used for the forward propagation of the dummy data during the gradient inversion attack. As a base frame, here we can see the basic gradient inversion attack as we discussed it before. Now, for each dropout layer, the corresponding dropout mask is initialized randomly from a Bernoulli distribution with a probability of p. And instead of solely optimizing for the dummy data, the attacker now jointly optimizes the dropout masks and the dummy data. If we jump back to our schematic representation of dropout masks and corresponding features, we see that the attacker may not find the exact same dropout masks that the client used during training. However, he may find a close enough approximation of the masks, which, as we will see in a few moments, is sufficient to be able to reconstruct the client's training data. To systematically evaluate our proposed approach, we investigated different model architectures, datasets, as well as different client batch sizes and dropout rates. For each dataset, we randomly select 128 client training images to be reconstructed by the gradient inversion attacks. We evaluate the attack success by first calculating the client gradients from the client images. These gradients are then attacked by the gradient inversion attack to obtain the reconstructions. Finally, we calculate the structural similarity, or SSIM, between reconstructions and original images to measure the reconstruction quality. High SSIM indicates high reconstruction quality and insufficient data privacy. In this first set of results, we compare the reconstruction performance measured in SIM of the inverting gradients attack IG, which is highlighted with the gray boxes, and our own proposed dropout inversion attack, which is highlighted with the orange boxes. Both attacks are conducted with a simple MLP and a vision transformer for the Cypher10 dataset. In this case, we look at an attack batch size of 1 for varying dropout rates. On the right-hand side, you can see a few reconstruction examples for the corresponding experiments. Note that for a dropout rate of 0, we did not attack with our proposed dropout inversion attack, as in this case, we would just default to the basic IG attack. We find that, in contrast to IG, our dropout inversion attack is able to successfully reconstruct client data from shared gradients even if dropout was used during the model training. However, the reconstruction quality decreases with increasing dropout rates. As you can observe in the illustrations for the vision transformer, the reconstruction quality is affected more notably for higher dropout rates compared to the MLP. However, we are still able to reconstruct recognizable images of high fidelity. Since our proposed dropout inversion attack jointly optimizes for dummy data and dropout masks, the number of optimized parameters is highly increased with the number of dropout layers that are used in the model. We therefore investigated the applicability of our proposed attack on a state-of-the-art sized vision transformer B16 and a practical image classification dataset, namely ImageNet. Following the recommendations of the original vision transformer paper, we apply a dropout rate of 0.1. And as you can see, even for such a low dropout rate, IG is not able to reconstruct the data. In comparison, our proposed attack creates well-recognizable reconstructions and achieves a mean SIM of 0.72. We further investigated the efficacy of our proposed attack on CNN-based classifiers if dropout is applied before the output layer. Consistent with related work, we used a Leakage and a ResNet. Our results confirm that for the baseline IG attack, the reconstruction quality decreases for increased dropout rates for both model architectures. In contrast, when our dropout inversion attack is used, we can successfully reconstruct client data regardless of the enabled dropout. Finally, we also assessed the efficacy of our proposed attack for increased client training batch sizes. Here you can see the mean structural similarities for both the MNIST dataset on the top and the Cypher10 dataset on the bottom for an MLP in the left column and the vision transformer in the right column. All images are attacked with our proposed dropout inversion attack. Dropout rates increase from top to bottom and batch sizes increase from left to right. As you can see, both increasing dropout rates and batch sizes decrease the quality of the reconstructions. Again, the vision transformer is more notably impacted than the MLP. We observed that when reconstruction quality decreases, the optimized dummy dropout masks diverged from the original client dropout masks. Therefore, to further improve the reconstruction quality of our attack, we introduced the dropout mask regularization term. During optimization, we regularized the dummy masks of the attacker to match the client's dropout rates. We performed another set of experiments with a fixed dropout rate of 0.25. As the SIM for the MLP is already close to 1, only marginal improvements can be observed upon adding our regularization. For the vision transformer, the added mask regularization shows a notable increase in SIM and hence improved reconstruction quality, especially for batch sizes that are larger than 1. More detailed results and discussions can be found in our paper as well as the supplementary materials. To summarize the key takeaways of this presentation, it is known that neural networks are prone to privacy leakage by gradients, and that common perturbations defenses come with an inherent trade-off between model utility and privacy. In our work, we formalized the use of dropout as one possible candidate for a privacy module that introduces stochasticity into the training process. Dropout causes an inherent mismatch between the model realizations of the attacker and the client. This in turn prevents the reconstruction of client data. However, this also offers a false sense of security, as an attacker can still reconstruct client data by approximating them with our proposed dropout inversion attack. Further work of our research group found that other privacy modules such as precode can be more effective. However, we found that a combination of complementary defense mechanisms should be applied in order to protect privacy and maintain model utility. I thank you for your attention, and I'm looking forward to meet you for interesting discussions. See you soon.